after the short summer break. My name is Rasaya Kaitis. I'm media manager at Sinovoltaics, and I will be moderating today's webinar on the latest ultraviolet-induced degradation developments. Before I introduce our speakers, a few quick notes. This webinar will last about 1 hour, and 2 expert presentations will be followed by a Q&A session. On the right-hand side of your screen, you can see the Q&A chat. So please use the Q&A chat to submit your questions at any time during the presentations, and I will address them at the end of the 2 presentations. This webinar is being recorded and will be uploaded on Sinovoltaics YouTube channel. If you don't want to miss the newest content updates on YouTube, don't forget to subscribe to our channel. And now let me introduce our esteemed speakers. So it's my pleasure to have Professor Bram Hooks today in this webinar. He's a Deputy Head of Research at the University of New South Wales School of Photovoltaics and Renewable Energy Engineering. Bram is the lead researcher of the recent study on ultraviolet-induced degradation, which made headlines this August. And in today's webinar, he will share exclusive insights and findings of that research. During a test run we had yesterday, together with Nicholas and Bram, Professor Bram mentioned that some of the insights he'll present today might be shared with the public for the very first time. So we are extremely lucky. He's also the author of more than 300 scientific papers and has been widely recognized for his contributions to the solar industry. Another expert in today's webinar is my dear colleague, Nicholas de Weimar. As Chief Technology Officer, Nicholas is in charge of the technology development at Sinovoltaics. He was also in charge of developing our proprietary artificial intelligence-driven electroluminescence imaging software that we call SELMA, which allows us to perform 100% PV module inspections at the factories. Nicholas has been active in the PV industry for more than 15 years and has a track record of over 100 PV manufacturers audited in East and Southeast Asia. Today, Nicholas is dialing in from Malaysia, but he resides in beautiful Hong Kong. And Nicholas will briefly cover the UVID reliability challenges and explain how industry is already adapting to this new reality. Before I hand over the virtual mic to Nicholas, I would like to briefly introduce Sinovoltaics. Sinovoltaics is a Dutch-German company specializing in technical compliance and quality assurance for both BESS and PV industries, and we operate globally. Our services include quality assurance inspections, factory audits, ESG reporting, and traceability audits for utility-scale solar and BESS developers and investors. We provide these services across all key components typically found in large-scale PV and BESS projects, including inverters, components, transformers, etc. And with more than 15 years of industry experience, we have audited over 350 PV and BESS factories worldwide. And final note from me, before I let our esteemed speakers present, if your work field also includes battery energy storage systems, make sure you register for the webinar that will happen next week. 2 experts will share real-life case studies on how smarter BESS factory acceptance testing can help you save millions in utility-scale BESS projects. I'll pop the registration link in the chat just now. As we have a very hot topic today and top-tier experts, make the most of them, ask questions, get direct answers from them. And now I give the floor to Nicholas.
Thank you, Raza. Good morning, good afternoon, and even good evening, everyone here. First of all, I would like to thank you for joining us today. It's great to see so many people. We actually have over 570 participants from different parts of the industry, developers, asset owners, researchers, manufacturers, and from over 30 countries such as Australia, Japan, Switzerland, Germany, China, Norway, South Africa, Ecuador, Singapore, Qatar, and so on, all coming together around this topic of UVID. And indeed, TOPCon and also HET have increasingly gone from emerging to mainstream faster than almost anyone expected. That's very exciting, but as we all know, every new technology generation brings new reliability questions. We have seen the challenges with PID, with LID, LETID in the past. And now with UVID, we are facing the next one. UVID is no longer just a laboratory curiosity and is in a complex way linked to the design of a PV module beyond just the cells, but especially with regards to the encapsulant materials and passivation layers. We are starting to see evidence in real production, and that makes it a genuine risk for long-term performance. And for asset owners, that translates obviously into financial risk if projects don't deliver the expected energy yield over 20 to 25 years. So on the ground, we are also seeing very practical bottlenecks. For example, UVID is relatively new in the spotlight and not yet fully standardized in testing, which creates uncertainty for buyers and asset owners. Labs and manufacturers are actually still racing to develop reliable test protocols, but bottlenecks still exist, and that includes also long queues at laboratories, and there's also lack of harmonization in methods. Right now, if you try to get actually UVID testing done at some labs, you're often facing long waiting times of months just to even get a testing slot. That's valuable time lost in fast-moving procurement and project development cycle. And the demand from what we see currently is so high that for cost and probably also in time-saving reasons, some developers choose to run UV60 tests instead of UVID. At Sinovoltaics, we have been addressing that challenge in a practical way because of our long-standing relationships with reputable labs, with our UVID reliability testing packages in partnership with accredited laboratories. We are able to arrange UVID testing without this queuing time. This year alone, we have already supported 7 projects focused specifically on UV-related tests, covering alone almost 700 megawatts of capacity. And these aren't theoretical studies. They are real commercial projects where developers and investors require answers before making final decisions. And considering that with UVID, it's crucial to identify suspicious bill of materials. The point is, the faster and more reliably we can test, the sooner the whole industry can move forward with confidence. New technologies like TOPCon can be promising, but if you don't get the reliability piece right, then we risk basically undermining all that progress. Especially for N-type TOPCon, UVID has emerged as a significant concern, and that's why we also sit here together to dive deep into this topic. And even though without the worry of boron oxygen LID, some TOPCon modules can be susceptible to cell-level UVID, especially when combined with UV transparent encapsulants. That's why today we have this very important and valuable session. We are fortunate to have it together with with leading experts in this field, and specifically our research partner, Professor Bram Hoeks from the University of New South Wales, who has been doing pioneering work to deepen our understanding of UVID and to point the way towards practical mitigation, and sharing also today brand new insights on UVID with you today. So with that, I would like to hand over to Professor Hoeks. Bram, now we are all looking forward to your insights.
Okay, thank you very much, Nicholas, for the very good introduction for this important topic. And I see my slides have appeared on the screen. So today I will share our latest insights on UV-induced degradation. And most of this work was done with our industry partner, Canadian Solar. And part of this work we will be presenting for the first time publicly next week at the European conference. So you're getting a sneak preview of 2 of those talks. We've seen a very rapid transition from PERC to N-type technology, in particularly TOPCon, and yeah, it's right to say that they're dominating the market now, and will continue to dominate the market for the near future. Unfortunately, there's a lot of not so good news appearing in the media. So various testing agencies are releasing these kind of messages that there are reliability risks. So PV Magazine, often based on publications from research institutes. So there's really something that we should look deeper into. So TOPCon, we should ensure that these concerns are properly addressed and properly understood. What is really the concern, and can we do something about it? And we hope to give you some insight today in the presentation. It is also confirmed by testing labs, so PVEL and RETC, where we see, particularly for TOPCon, and the main concern is that like we see an average reduction, but also some outliers that even show like 10%. So there's really a high variability, and that's an indication of that the problem is not yet fully understood. So we still have a way to go to bring it up to acceptable levels. A major concern for UVID is that it's metastable. So if you do the typical stress testing, and then put the samples away after stress testing, and you measure them after a few days, which is quite common, you see that your measurement is quite severe. So in terms of tissue loss, but it can actually be improved by light soaking, and it can be improved by just measuring several times. So this just indicates a metastability. So this was work done by colleagues at Fraunhofer ISE, I think, where they showed that you can also switch on and off this metastability by light soaking and putting them in the dark, light soaking, putting them in the dark. So again, an indication of metastability. And in this presentation, we will show you actually what is the root cause of this metastability. Another insight that they showed is just by flashing them many times, you can get to a steady state value that is probably more representative of what you want to measure. But it also depends on the flash settings, and this was not fully explained in the paper, but that's something we're still working on to understand why there's such a difference between flash durations in this case. But I think what we want to work towards to something that we do appropriate stress test and then measure at field relevant levels. And at the end of the presentation, I will show you the current status of the standard development, which I will actually be presenting in a lot more detail next week in Bilbao at the EU PVSec. Should we care about it if it only happens at testing labs? So unfortunately, it's not only in testing labs. So this is results from fielded modules. These were fielded NPERT modules. They have exactly the same front as the TOPCon solar cell. And this is a study by NREL, just published, I think, a few weeks ago. They showed 2% power loss per year. So that's a lot more than the 0.4 that was on the spec sheet. So really a concern. Fortunately, they had some unfielded spares, which allowed NREL to do some great work to look into the insights. And the first insight they got was these cells actually had, these modules had 2 issues, and they were shown in 2 different ways in the solar cells, actually. So the EL images and IV measurements confirmed a significant increase in series resistance. This is not typically something associated with UVID, but I will explain later why this is relevant. The PL images, so that's photoluminescence, where you're not extracting or injecting any current, these are shown here, show also a decrease, and that's the normal UVID that we see. So UVID normally affects mainly the VOC. So it increases recombination, reduces VOC. But what is this combination that we both see, VOC loss and series resistance loss? This was studied in a very clever way with a non-fielded product. So what they did, they exposed half of a module to UV, and half of the module they did not expose to anything. So you can do a relative comparison, and they saw that with UV stressing, they saw 6% loss, which is significant. And this was probably around like 120, oh no, so 600 hours, but like 6 years equivalent dose. So that's quite substantial. So 6% loss, we would not be happy with that. But if we do a combination of damp heat testing and UVID, we see a significantly larger loss. So this is a loss of 29%. And that's the combination of VOC and series resistance. So UV-induced degradation can also affect the encapsulant. And in this case, the encapsulant was releasing acetic acid that resulted in series resistance issues. So this really shows that combined stress testing is definitely something we have to move towards as a sector. I will not show it in this presentation, but it's something I'm quite passionate about, and it's definitely something that's shared by also Sinovoltaics and the great group at NREL. So if we then look at like understanding the fundamentals of UVID, we focus on the component that is the main culprit. In this case, it's the cell. The cell is sensitive to UVID, and let's see if we can understand the UV sensitivity of the cell a bit better. And I'm looking at a few questions here. So does the UV spectrum affect UV-induced degradation? For TOPCon, should we care about the front and the rear, or is one of them more sensitive? And this is more a fundamental question, but the firing step that we always do in manufacturing, does it actually affect UVID? And this actually gives us part of the puzzle to solve the mechanism, as I will show you later in the presentation. So what we did, and this was work that was published in August, we did stress testing with two different light sources. We had UVA, so that's harsh UV, but then we go harsher with UVB. So there's two different peak wavelengths, and the dose and the power was kept roughly identical. And you can see, if you compare it to the AM1.5 spectrum here in the red, is that the AM1.5 has both UVA and UVB. So we see, we were checking if we use the same intensity, if they would show the same degradation. So this was the result with UVA. So it's still harsh UV. I would not be happy being in that climate chamber myself. And what we saw is that in this case, we looked at the effective lifetime of lifetime samples, and we saw reduction of the effective lifetime. So we saw UV damage, and this UV damage we could mostly attribute to an increase in the saturation current density, in this case, the surface. So we saw significant damage due to UVA. But the interesting thing is that we only saw this damage at the front. The rear, we did not see anything. And we could attribute the whole increase in recombination was due to increase in surface recombination. So no bulk defects in this case. If we then look at UVB exposure at the same temperature, we say that in this case, we just plot the saturation current density. So that's the recombination current. We see a massive increase. And we see here a significant difference between the fired and the unfired sample. The fired sample is more stable than the unfired sample. And this is something we will come back to. So this explains, this is one piece of the puzzle in understanding the mechanism and also how to address UVID at the cell level. The experiments with UVB again confirmed that the rear side of the TOPCon doesn't show any degradation. I must must stress that these TOPCon cells have a relatively thick polysilicon layer, so 100 nanometers plus. So all the UV is basically absorbed in the polysilicon. Once we move to polyfingers, this will be different. So then the rear could become sensitive to a UVID. And yeah, I already mentioned the fired sample, less degradation than the unfired sample. So if we then look at, coming back to the spectrum, so we had the same intensity in terms of watts per square meter for UVA and UVB. And then if we look at how much we have in this, the AM 1.5 spectrum, is the majority of the UV is actually UVA, and only 1.5% of the UV is UVB. But if we look at the damage, and it's quite a complicated graph, but the main thing you should take away from this is that we see if we take the identical ratio that we have in the AM 1.5 spectrum, so our dose is calibrated to replicate an AM 1.5 equivalent exposure, we see that the vast majority of the damage at the cell level would be done by UVB. So this means, and this is also confirmed by other work by Enrel, for example, is that it's really about the higher energy photons that are doing most of the damage. So if you can reduce the intensity of those reaching the cell, you will improve your UV resilience of the solar cell. And the difference is very remarkable. So really, most of the damage is done by UVB. So we've already had some answers to the initial questions I posed. So are all photons created equal? No. High energy photons create significantly more damage. And this is something we're working on to quantify that even further. Is the TOPCon front and rear, do they have the same sensitivity? No. The front is very sensitive. And that's why in the remainder of my presentation, I will mainly focus on the front of the TOPCon solar cell. So we will really narrow down on what's happening at that interface. The rear is not sensitive because all the UV is absorbed in the polysilicon. Details can be found in the paper. This will change if we go to polyfingers because then the rear becomes sensitive again. Does the firing process have an impact? Yes. Firing makes your cells more stable to UVID. So it shows you one of the knobs we have to make the cells less UV sensitive. And for this, to explain this, we have to go a bit back to fundamentals. So if we look at surface recombination, so this is the recombination fundamentals, it's governed by two different processes. So you have interface recombination, where the recombination rate, so in this case, the surface recombination velocity, it can be surface saturation current density as well. It's basically equivalent. Just depends linearly on the number of defects you have. And in this case, is quantified by the interface defect density, where for top passivating films that we use are around 10 to the 10 defects. So it doesn't mean you have 0 defects. You just have a lot less than if you would not do anything. So if you don't do anything, you have roughly 10,000 times more defects. The best we can achieve, is 10 to the 9. So that's with thermal oxide. So this was used in the UNSW world record PERC cells in the late 90s. But the typical ALOX film is in this range, so like 10 to the 10, 10 to the 11. Because most films also rely on the second part, which is field effect passivation, where you have fixed charge in your dielectric that either if you have a negative charge or a positive charge, they both can reduce recombination, because for recombination, you need both an electron and a hole. And if one of them is short supply, then your recombination rate goes down. So with negative charge, you push away the electrons, and that reduces the recombination with the electron concentration. And this is super important to understand what's happening with UVID. So we'll come back to this, to DIT and QF quite often in the remainder of this presentation. If we then look at ALOX, so this is ALOX is used in 100% of the TOPCon front. So that's why it's important to look at this interface. And how does ALOX provide surface passivation? This has a fixed negative charge that is present at the interface with the silicon oxide, which is unintentionally grown on crystalline silicon. So the negative fixed charge is here. And then your interface defect density is determined by the quality of your silicon oxide. So that determines your DIT. The fixed charge in your ALOX determines your field effect passivation. And both factors are affected in UVID. And we actually already knew this in when we first started working on ALOX. So this is work that I did when I was still a grad student in the Netherlands, where we looked at like a very exotic technique to measure electric fields in silicon. I will not bore you with the details. The only thing you have to take away is that we can measure electric fields, and that's exemplified here when we had a sample where in the acid-positive state, we knew that there was no fixed charge. With annealing, we could switch it on the same sample, and we saw a massive increase in the EPCs signal, so the electric field signal. So we had a non-contact way to measure electric fields. What we also saw in this experiment, and this is super relevant for this study, is that if we took a too high intensity laser beam, the EPCs signal increased. So we were able to kick electrons from your silicon into the ALOX and increase the fixed charge density. So we already demonstrated at this time that the fixed charge density is not necessarily a constant. You can increase it. And this is happening in UVID, because the more energy the photon supplies, the higher it's kicked up initially, and the higher the chance it actually can get trapped in the ALOX film. So we had here the first direct evidence of charge injection into ALOX. So now we have a few new research questions. So I told you that QF and DIT is super important for surface passivation. So can we actually quantify that during the various stages of UV-induced degradation? Does the aluminum oxide thickness and preparation method play a role in UVID? And can we actually also happen what is causing, I will show you, there is some difference in DIT. Can we explain what is happening there? And all these questions we will answer in the next slides. So we set up quite a complicated experiment, and I will not bore you with all the details, but we take two types of samples. So one more conventional lifetime sample that just allows us to do more sophisticated measurements, particularly to extract DIT and fixed charge. And we take the sample that is representative of the front of the TOPCon solar cell. Then we again test firing versus non-firing, and we test two different thicknesses of ALOX. So these are ALD ALOX films, 4 nanometers, which is more representative of what people would use in industry nowadays, and at 7 nanometers. And then we use accelerated testing using UVB, because that gives us the result very quickly. We look at the effect of dark storage. We look at dark annealing that has been shown to recover it. So I will show you some concrete evidence of that later. And then we also look at what would happen if you would measure the sample a few times. So we'll show that that's actually equivalent to exposing it to UV. So if we first look at the accelerated UVB testing, we see that both samples, so the lifetime sample and the sample that is more representative of the front of the TOPCon solar cell, show an increase in recombination as a function of UV dose. But we see two separations. We see that fired samples do better than unfired samples. But more importantly, this thicker ALOX film, and this has been shown by other groups as well, significantly less UVID. So that's the first mitigation method that we have available to us. Go thicker with your ALOX film, you will have less UVID. And we're quite confident that this is already used in the industry to produce more robust samples in terms of UV sensitivity. Then this was work done by Fraunhofer in Germany, where they compared ALD versus PCVD alloys, and there was a massive difference. So PCVD alloys with a PCVD silicon nitride stack, significant reduction. So that's the yellow curve here. Reductions up to 27% after quite an impressive UV dose. So that's 100. So that's 140. So that's well beyond 120, which is probably the most strict testing that's typically reported. But then if we compare to plasma ALD alloys, so the only difference is with how the thin alloys layer is prepared. We see that that one is a lot more stable. So this is more comparable to the results we showed earlier. Our testing is a lot more extreme, so that's why we saw recombination. But they also show that if you just make sure that your silicon oxide film is of higher quality, in this case they used thermal oxide to make the silicon oxide layer, while in these two cases they rely on the silicon oxide that is formed during the process. That also made the cell a lot more stable. So this clearly points towards making sure that you have like a very good interface that so the quality of your interface will determine how sensitive you are. So key trend, PCVD, really a poor performer in this case for UVID. Plasma assisted ALD, which is I think there's only one company that I'm aware of supplying that equipment for the industry. Most people would be using thermal ALD, but thermal ALD you would expect roughly something similar, so a similar result as PEA, plasma enhanced ALD, and thermal silicon oxide stacks, which is also something you could easily implement in manufacturing. If we then look at what is happening with this recombination current when in the various stages, and we come to like dark annealing of dark storage later. So we see that on the UV exposure, we see the recombination current ramping up. But then in dark storage, we see that this doesn't stop. So this is fully consistent with the results reported on solar cells and modules, where dark storage results in a further reduction of the performance, so an increase in recombination, decrease in VOC. And we see that there's a bit of scattering in the sample, so we see that the sensitivity is not uniform, but the worst performing samples, they really see, particularly this one, a rapid increase in degradation. And then in dark annealing, which is done at 85 degrees, we see that we can basically get it back to the normal value. So 85 degrees is, of course, higher than you would typically see in the field, but it's again an important piece of the puzzle. What is causing this degradation? So now we come to the more like the very technical results, and this is something most companies would not have in-house to measure the interface defect density as a function of treatment. So, and I will guide you through it. So first of all, on the UV exposure, we see a rapid increase of DIT for every sample. So these are the different samples, so not fired, two different thicknesses. The detail actually doesn't matter because they all show the same behavior. UV breaks silicon hydrogen bonds, which is one of the weakest bonds in the dielectric stack. And this hydrogen, I will show in the next slides, it actually accumulates at the surface. So we break silicon hydrogen bonds throughout the stack, but the mobile hydrogen piles up at the interface. In the dark, we see that for most samples, so here we see a slight increase, but most samples we see DIT staying equal. So there's nothing happening with DIT when you put the samples in the dark. So that's a very important observation. It's also not improving. It stays stable. If we do the annealing, so that's the green curve here, we see that we improve the DIT. So we fix the interface, and we attribute that to hydrogen diffusing away from the interface. and we can see that we're back to square one. And then a short UV dose, as you would use in like stabilizing before measurement, doesn't really do anything for DIT. So it means we have part of the puzzle, but we don't have the full puzzle for DIT, if we just focus on DIT. And this is the evidence we have for this hydrogen piling up at the interface. So these are time of flight SIMS measurements. So we're counting fragments. So we remove a layer and we count what is removed from the layer. And then we count the mass, and then we can assign certain fractions we measure, we can assign to hydrogen. And we see that in this case, we see a significant increase after UV at the interface. So we see hydrogen piling up at the interface, and it's not very well known, but like experts in the field know that too much hydrogen is not good. Too much hydrogen actually creates defects. So like a low amount of hydrogen is good. It's good for passivation. You can have too much, and that's what we believe is happening here. But yeah, we don't have the full solution. So we also have to look at the fixed charge density. So under UV, QF increases. In dark storage, this charge actually is released back. So in the dark, the additional charge you pump into the system is released. And this is something we also already showed in 2008. So it's not really new for us. But you see consistently that you pump it up, it leaks out, and that is the main cause for this dark storage reduce in passivation. The anneal, counterintuitively, this actually reduces QF. And this is also well known for people like myself who have spent more than enough time on the analog system, is if you anneal the system for a longer time, you typically end up with a lower fixed charge density, but you fix the DIT, so overall your passivation goes up. And a short UV dose is again enough to increase QF. So this preconditioning that we see all has to do with QF. So the full dark storage is explained by QF leaking away. This preconditioning is just bringing the QF to the level it would also be in the field. And that's important. So we should measure UVID at the level that is field relevant. I will come back to that later as well. So, and this is like the evidence where we also showed that, we can increase. So in this case, with second harmonic generation, we can see this charge injection. Here we switched off the laser beam for a while, and we can see the direct evidence that the part of the charge was leaked back into the silicon. So this is very consistent with the current with the understanding that we have for the system for almost 2 decades. We also looked at the chemical bonding of the dielectric film, and I will not go into much detail here, but we see that we have permanent changes in the film, which is quite remarkable. The changes are happening at both at the surface, and this is something that's probably a testing artifact for us because we test in air. We see that the silicon nitride actually oxidizes at the surface, also reported by other groups, but that would not happen in the field because there's not enough oxygen probably there to for this to happen, and it will also not be relevant for the surface passivation mechanism. What we see in addition is that even though our temperatures are very modest, so this peak 4, that increases in intensity. So we see changes at the crystalline silicon interface. So we see the silicon oxide, like the thermal oxide reported by the Fraunhofer group, we see that UVID, if like the various treatments that we do for dark annealing, for example, improves this interface and just makes it better for subsequent exposures. So if we come to our proposed UVID mechanism, it's actually quite simple. So UV breaks silicon hydrogen bonds. This hydrogen piles up at the interface, resulting in an increase in DIT. The UV also increases QF, but the increase in DIT dominates the passivation behavior. So that's why passivation decreases for the typical stacks that we have. In the dark, DIT remains constant. Charge that you pumped in goes back to the steady state condition. So increasing recombination. Fortunately, you can recover that. So if you anneal, you actually fix DIT. If you expose to UV, you fix the QF, so you increase the QF again. So that's our current understanding of UVID, explaining all the meta stability, and this is informing the standards as well. So we can answer the research questions we posed. So can we quantify what happens? Yes, and I explained that in the previous slide. Can we do something? Yes, thicker ALOX films work better, and ALD films work better than PECVD. So this is very actionable insight for either you as a solar cell producer or as a buyer to ask for ALD films. And can we explain what happens at the interface? Yes, we believe that it's hydrogen accumulation that is the root cause, and that's why it can be fixed at relatively low temperatures. So currently, I've only focused on what's happening at the cell level. Of course, quite a popular approach, particularly for heterojunction, is to use UV conversion film. So this is provided by, for example, the company Cybrid with their Rabo product, where they look at a material that absorbs UV and then emits light at a higher wavelength, so at a lower energy. So it takes it from a regime where it's harmful for the cell to a regime where the cell is not affected. And that shields the cell from the harmful wavelengths of UVID and should have improved long-term efficiency. And this is shown here. This presentation I could find on, probably that's a typo, but the Tanyang News, they did recently, where they show that the Rabo product has the transmission properties of UV blocking encapsulants, but the EQE properties of UV transparent foil. And these are results that I believe were on TOPCon, and they showed that the modules were more stable. However, so this is something, it's a relatively new product. Of course, we have to confirm that it's actually long-term stable in the field, and we have to do multi-stress testing. So that's still, the jury is still out, and that's something we will also look into in incoming times. So the final part of my presentation, because we're almost at half an hour. So where do we stand at the UV standard? We have a lot of debates on what UV light source we will use. And if you reflect back on my presentation, it's very important how much of UVB do you have in your light source, because that does all the damage. And the standards have quite a wide range that is accepted and acceptable. So you can actually only compare apples to apples if you use the same light source. And then there's some other concerns as well, which I will come back to in the later slide. So it's very important that you compare similar or identical sources and conditions. We also see that we have to operate the modules near maximum power point or open circuit, not at short circuit, because there's significant differences. And the post-light soaking is needed to remove the dark source metastability, because we want to measure something that is field relevant. And the standard will not test to failure, but it will test up to 3 years outdoor, depending on where you are on the planet. But that's just, we have to remain practical. This is how the standard looks now. I will not go into detail. The slides will be shared, and the presentation, the recording will be shared, so you can pause here and have a look. And if you're in Bilbao next week, then I will explain it in a lot more detail. So in terms, sorry, I went back. So the lessons we've learned, and this is also something I will explain in detail in the presentation next week, is, or actually this one I presented today, UVID, really, it's all about the high energy photons. Your UV actually affects everything. So the filters you use, the meters you use, the housing. So you really have to calibrate and test at a regular basis, because your test done in March could be different from May. So operation really affects UVID. So you have to keep it at open circuit, which is the easiest, or maximum power point tracking. And yeah, you need a certain dose of, actually, it's only UV light that it's needed to bring the cell back to life. And the aim for the standard is to really predict what's happening in the field. So to conclude, UVID is a significant degradation mode. We made a lot of good progress, but there's still more work to be done to bring it down. We believe that it's best to see if we can solve it at the cell level, because then if it's solved at the cell level, it just gives us more freedom at the module level. Unfortunately, UVID is metastable for TOPCon and heterojunction. The metastability is quicker in TOPCon than heterojunction, so the standard will have to reflect that. For TOPCon, it's all about what's happening with DIT. So UV increases DIT, but also increases QF, which is metastable and which explains the dark storage. This is something directly actionable for you. So the ALD ALOX shows better results. Thicker is better. And that's how I've seen many companies already improving the UVID of their solar cells, which will translate to better modules as well. UV converting encapsulants are definitely a very interesting option. We have to look at the long-term stability. And then we're working hard on the standard, and we try to really address fully metastability. So we only report field relevant results in a way that can be done at a relevant time, because that's what the field needs. And this concludes my talk, and we still have 10 plus minutes for questions. So we'll stop sharing my slides now.
Thank you, Professor Bram, for such a deep dive into this hot topic. And the questions that we received and the number of questions that we received also signifies that this is a really interesting topic and important topic for the people working in the solar industry. So perhaps let's deep dive into the question section now. So I have a question from Tebayoti, if I'm pronouncing it correctly. So the question is, currently only light stabilization is performed during the creation of the calibration module. Do you think UV stabilization is also necessary? Question to you, Bram.
That's a good question by Deb. I think it's my former colleague, Deb, I reckon.
Okay.
Yeah. So I would say for a calibration module, I would probably recommend not to expose it to UV, because this metastability will just make it really a headache to. So definitely no exposure, but I would look at the metastability in the as received state without exposing it to too much UV. And it depends on your cell test or how much UV you actually have. So also the results that I showed were multiple flashes change the performance of your module. That's likely due to the fact that it's only the UV component that works towards that. If you would flash with UV, you would bring it up to a higher level very quickly. What we see in our stress testing as well, that we need to have a certain dose to make the module metastable. So I would say if the module is not exposed to a lot of UVID, it's not very likely to be metastable. So I would not expose it to UVID for your golden module. That would be my recommendation now. Yeah.
Okay. Thank you, Professor Bram. Another question from Usman. Which technology has more degradation or is prone to more degradation? Heterojunction technology or TOPCon?
Yeah, from the previous results, they're probably quite comparable. Although the typical heterojunction module solves it in the BOM, so like this UV downshifting material that I've shown, that is almost used in every heterojunction module at the moment. So currently, the TOPCon modules would show a higher sensitivity because, yeah, it's not addressed at the BOM level. Then the question is how stable, what's the long-term stability of these solutions? For heterojunctions, it's a lot more complicated because the metastability is slower, and we have a lot more hydrogen. So the hydrogen content, and I'm sure that you appreciate that, like we believe that hydrogen is at the core of LETID, in addition to the charge that bumps around. So I think for heterojunction, it will take a little bit more time to solve it. TOPCon, I think, with like the guidance already given this presentation and further work on the interface, we can bring it down with the right bill of materials. So I think it's a solvable issue. Yeah.
Thank you, Professor Bram. You, in the conclusions, you also mentioned that the thicker aluminum oxide layer, the better. But Shubham is asking if you know what optimum aluminum oxide thickness you recommend.
No, we haven't done a full split, and that's probably also my former colleague, Shubham. Yeah, that's something I would run at the design of experiments for the companies. Like we're giving guidance here for rapid testing. Our UVB testing, for example, is very rapid at the cell level, giving you quick feedback. You can then correlate that to module level. And we see as well that there is definitely seems to be evidence that you will eventually reach a steady state because of and that's consistent with our model as well. So the hydrogen piles up at the interface, but it also leaks away. So you have a balance of transport of hydrogen to the interface and from the interface. And I think that will be the key for your steady state reduction. So the NBRL result showed for that very old generation and PERT that ended up at 6%. And that's, if I remember correctly from the presentation, that stabilized there as well. So I would say that would be just running experiments. We clearly showed that for the tool we used, that 4 was a lot better than 7. Yeah, if 8 is going to be better, I don't know. We haven't tested it. Yeah.
All right. Next question is from Jelach. Can UVID be prevented by better passivation to reduce recombination rate?
I'm not sure if I completely understand the question. So we have to make sure that the passivation of the alloy silicon nitride stack is very good. Like that's why it's dominant, and in combination with a boron diffusion, it's already very good. So I don't think we need something better. It's about, can we use something that's more stable? Yeah, that would be good. And then we believe that the allox layer is actually a hydrogen barrier, which we have demonstrated several times already. So just having the allox film, which is hydrogen lean, it's a barrier for the hydrogen transport from the silicon nitride film. So that's a way to make the cell more stable. And we've also working on stuff that I cannot comment on yet, which would potentially make it completely stable. So there's definitely more work we can do, but I think with the current tools we have, we can already bring it down significantly. Yeah.
All right. Another question that I have is, what's your recommended testing conditions for UVID test? Is it worth doing UVID 60?
Yeah, I would go as high as you can tolerate. I would say 60 is even not enough. So 15 kilowatt hour, and that depends on your spectrum as well, is 50 days in Arizona. So that's not even 2 months. Yeah. if you increase that to 60, then you're at 200 days. Would that be enough to warrant 200 of 25 years? Yeah, you don't need a degree in math to say that that's not enough. It's also for like, I don't think it's enough to reach the steady state condition as well. So I think 120, that's also what the standard is pointing towards. That's what people feel comfortable in terms of what's doable and what is an appropriate assessment of the risk. And of course, groups like my group will keep pushing our understanding to see if we can maybe by tweaking the spectrum, because currently I could not go into the detail, but the range, the tolerance we have in spectra still makes it the 120 done by lab A is not the same as 120 done by lab B. And if you want to report good results, I can help you design, like, no, I'm joking, but I can help you design the spectrum that that will give the lowest results to your clients. Is that good for the industry? No, but you would still be in the standard, and so that could easily be a factor of 4, probably more. So that's a bit scary as me as somebody who intimately understands it and cares about reliability. We want solar to perform, be a reliable source. It's going to be the main source powering our future. We have to make sure that the public maintains confidence in renewables and general PV in particular, because if we lose the confidence from the public, it's very hard to get that back. So we should have the appropriate standards that predict whatever asset life we're aiming for. So if that's 20 years, ideally longer, because that's it's always better to squeeze more out of an asset. So that's more a philosophical answer, but yeah.
That's very well said.
Yeah.
That's very well said, Bram.
Sorry.
And I think we at Sinovoltaics also strive for quality, and that's why we do what we do. We perform quality tests. This is a nice, I think, ending as we are almost running out of time. We still have around 10 questions in the question box, so we will answer those in writing and share the answers with the audience. Let me just ask a final question to you, Bram. That is coming from Dricus. He is thanking you for this deep dive on UVID and is asking whether, aside from research on UVID, is there any other topics that at your attention at the moment at the University of New South Wales?
Yeah, in terms of reliability, the corrosion. So we look. There's so much movement in particularly in metallic paste. So with laser-assisted firing now being generally adopted, we see that as something we just need properly to understand for compatibility of the bill of materials. And then also we're quite active in developing also novel UV conversion technologies. So and we're also working on technologies that ideally would give 2 photons for every UV photon. So in order not only to protect the solar cell, but potentially to increase the solar cell efficiency by applying a more active like current generating of a current generating component either directly on the cell or in the module. So and then of course we have a massive tandem portfolio. So we work on every tandem technology that is under consideration, because we're getting close to the fundamental limit of silicon solar cells. That's also why we actually become more sensitive to these failure modes, because every additional FEM2M, it's quite a technical term, but for a PERC solar cell, 5 FEM2Ms in additional recombination, you would not see it. So that was one of the questions I saw as well. For a TOPCon solar cell heterojunction, it kills you. So the closer we get to the fundamental limit, the more sensitive we become to failure modes that maybe were already always there, but just we were not sensitive to them. And then the next step will be tandem. But there we also have concerns with perovskites in terms of stability, where there's a lot more than just UVID. I can tell you that.
Well, thank you. Thank you once again, Professor Bram, and thank you, Nicholas, for shedding a light on the latest UVID developments. I thank you, the audience, also for being so engaged. We'll provide you the answers to your questions in writing, and also we will share a recording of this webinar. If you have any questions, don't hesitate to contact our esteemed speakers directly. You can see their contact details on the screen. And I wish everybody a great day and see you in the next Sinovoltaics webinars.
Thank you. Bye-bye.
Thank you. Bye-bye.
Visit sinovoltaics.com to learn more.